Hello, dear friends. This is Mechanical Vibration Lecture Series 7. In today's lecture, we are going to see the response of damped system under the forcing function f of t is equal to f naught e the power of I omega t. Means this is exponential type of function. So in last in previous lecture, we have seen the forcing function is a sinusoidal function, that f of t is equal to f naught sine omega t. So let's see for the exponential function, f of t is equal to f naught e the power of omega t type. So this is also another form of solution for the forcing function. So let's see. So the forcing function be represented in complex format in this type. So that is because we have this I, or sometimes we can use it as J, okay? So is a power of I omega. So this I indicates the complex conjugate form of expression. So exponential form in the complex format. And the governing equation of motion becomes mx dot dot plus cx dot plus kx, which is equal to f naught ei or I omega t. So what we are looking here is the damped system with forcing function. So our forcing function f of t is equals to this, and we have damping system, viscous damping coefficient is there, mass is there, and the elastic constant k, that is stiffness, is also there. So this is general form of equation in this case. And now by assuming particular solution, so we have two type of solution for such kind of equations. As we have seen in the previous lecture, we have homogeneous solution and the particular solution. And homogeneous solution is when this forcing function is 0, then mx dot dot plus cx dot plus kx is equal to 0, then we have homogeneous solution. And whenever we have forcing function like this, f of t is added on it, then we have another solution called particular solution. So that is the particular solution must be in the same format to the forcing function here given. So our forcing function given is in the form of exponential complex form. Therefore, our particular solution also in the form of that. It should be similar. Okay, so x of x particular of t is equals to x, the maximum amplitude of vibration x, times e the power of I omega t. This is the form of solution. And successively differentiating this function, this equation, we have x dot particular of t, that is the velocity term for representing the viscous damping, which is equal to I omega x is the power of I omega t. And then the acceleration term for the inertial component of our equation, which is x particular of dot dot of t is equals to I square omega square x is the power of I omega t. So I square is -1. So that is the complex form of equation. So I square implies that -1. So that we have minus omega square x e the power of I omega t is the acceleration. So there are some representation. The complex format with the trigonometric format. How we can represent? For example, I means, which is equals to cos pi over 2 plus I sine pi over 2 is the representation for I, which implies e is a power of I is a power of I pi over 2. So This means kind of definition for I. And actually, as we know, the numbers within radical is not represented with minus sign. But whenever such happen, that is the complex form of representation, so that minus of radical 1 represents I. Okay, so this is the definition of the complex form of representation. So now we have these three equations, 1, 2, and 3. And substituting these three equations into the main equation on the governing differential equation here, on second order equation, instead of x dot dot, we substitute this value. Instead of x dot, we substitute this. And instead of x, this will be substituted. Finally, we can find this equation, which is equals to, from the given equation, we can find x, which is steady state amplitude of the vibration, which is equals to f naught over minus m omega square plus IC w plus k. And finally, this is by rearranging these terms, real and real terms and the imaginary, because when we are talking about complex number, we have real axis and the imaginary axis. So that taking the real part and the imaginary part, then we have x is equals to f naught. F naught is this maximum amplitude of the forcing function. So f naught over k minus m omega square plus ICW. So this is the steady state amplitude of vibration. Okay, so now making some kind of mathematical arrangement, just multiplying this term means taking this minus of ICW means the conjugate form of this. The conjugate of this denominator, we multiply it. Actually, this is a simple mathematical calculation. So by the same term, finally what we can get is these equations. Okay. We can multiply this with this with this. Then what we can get, k minus m omega square, the whole square, plus cw square. So finally it is k minus m omega square minus ICW over k minus m omega square, the whole square, plus cw the whole square times f naught. Again, we have to separate the real part and the imaginary part. So this ICW part consider the imaginary axis on the complex numbering system. So k minus m omega square means this k and m omega square taken separately, minus I times CW k minus m omega square plus the whole square plus CW the whole square times f naught. So we have complex relation, complex conjugate relation, like x plus iy is equals to a times e I pi, where a is equals to x square plus y square in this expression. And this pi is tan pi is equal to y over x for this expression. So using this complex relation, finally what we can get, we have this equation, okay, directly taken from here, and finally we can get a is equals to 1 over k minus m omega square as whole square plus c square omega square, that is the amplitude of, okay. One can follow these steps because I already clearly define every term here, so one can see these steps. So finally, 1 over, we can say f naught over radical of k minus m omega square the whole square plus c square w square means cw the whole square, which is equal to xe the power of I pi. Then finally, this is the expression for the amplitude x. X is equals to f naught over radical of k minus m omega square the whole square plus cw the whole square times e minus e the power of minus I pi. Now we can take tan pi is equal to y over x. So our y is using the reciprocal representation. We directly take CW, this is the y component according to our representation, and this k minus m omega square over this thing was the x component, means here we have this is y and this is x. So no, not this is y and this is x. We can see it from there. Yeah. Considering this as x component and this as y component. Okay, this is the y part, this is the x part in our case. Okay, so from that relation what we can get, pi is equals to cw over k minus tan inverse of cw over k minus m omega square is the pi value. So finally, substituting the steady state amplitude x and the pi components in our equation, we will get the particular solution x particular of t is equals to f naught over radical of k minus m omega square the whole square plus cw the whole square ei e the power of I omega t minus pi. This is a general form of equation. This is the particular solution of the system. Okay. So this is something which we are searching for. Okay. So in that we have x is equals to f naught radical k f naught over radical k minus m omega square the whole square plus cw the whole square e minus e the power of minus I pi. So just taking k out from here, this k term out, once k comes out it will be here k over k, this over k, here also k square, actually k square, not only k, when k comes out here. So it becomes here f naught over k, the whole over radical 1 minus r square, the whole square plus 2 zeta r square. Why? Because we have, this is 1, omega square is there, and m over k is, it is 1 over natural frequency square, because as we know, omega n is equals to omega n square is equals to k over m. So it is m over k, so that means 1 over omega n square. So that gives, and the ratio r is equals to, omega, the forcing frequency omega over omega n, so that r square represents omega square over omega n square, and 2 zeta r is equals to cw over k the whole square, so that this cw over k is 2 zeta r. So that's, and this f naught over k is also represented with the static deflection of the system, so delta stat. This also can be represented with delta start. So we can put it like this. So then taking this term to here, we have x over f naught over k, which is equal to 1 over 1 minus r squared plus I to zeta r. So one can represent this as x over delta st, which is equals to this term, and this is called the magnification factor, okay, which is magnification factor mf. So this is the complex representation of the equation. So how we can represent these terms in graphical form? So in graphical form, we have real axis here, and we have imaginary axis here. Okay, so so in the real axis, k times x of t, that is the force due to elastic modulus or the stiffness of the material, will be represented here along the x. Then the damping force is perpendicular to the forcing function. It can be in this or parallel to this. We can construct it here. This is c x dot of t. So and then the acceleration or the force due to inertial mass is perpendicular to the damping force. So this is damping force. So which is represented here, m times x dot of t. Okay. So omega, the forcing function omega is here. Okay. So and the phase difference pi is represented the forcing function f of t with respect to x of t, which is given here pi. Okay, so and omega t in the this omega t is from the real axis to the forcing function. This forcing function f of t is equals to this f of t is equals to f naught is a power of I omega t. So it is this one. So this is a representation. Okay. So yeah. So harmonic excitation representation in a complex plane is like this. And so what it is, displacement is given as x particular of t, which is equal to f naught over k times the function h of I omega under the absolute value, which is times e to the power of I omega t minus pi. This is by the phase difference. Okay. X particular of x dot of velocity is x particular of x dot of t, which is equal to I omega. So which is a derivative of this one. So I omega f naught over k, the function h under the magnitude of the function h of I omega times e I omega t minus pi, which is the same as I omega times xp of t. Okay. And acceleration is the acceleration term. This acceleration term is which shows in the negative direction of xp of t with omega square. So which is I square omega square f naught of k h the magnitude of function h I omega e I omega t minus pi, which gives us minus omega square x particular of t. So this is the acceleration This is the velocity, and this is the displacement. So this is the complex representation of harmonic function. Okay, now let's see some important terms here. Some terms which are called quality factor and bandwidth. These are some important terms. What are those terms and how we can relate them? So when we talk about quality factor, for a small value of damping, like for example zeta less than 0.005, 0.05, and this is a small value of zeta or small value of damping. So x over x stat. This means x over uh, x over f naught over k. F naught over k. Means f naught over k is represent this delta stat, that static deflection of the system. So x over x stat maximum for very small value of zeta. So then this value, which is equals to x statics or f naught over k over 2 zeta radical of 1 minus zeta square. So from this x over delta stat, this is near to near to resonance point, so that this omega equal to omega n means that is the point of resonance. So at a resonance, the value of zeta goes to 1. No, this yeah. Resonance point means zeta is not 1 actually. It is omega over omega n, or r is equals to 1. R is equals to 1 in the resonance. At that point, we have 1 over 2 zeta, which is equals to q, we call q. This q is called the quality factor. So the value of the amplitude ratio at resonance is called quality factor, or we call it as Q factor. And it analogs to the with the electrical engineering applications such as tuning circuit of radio, where the interest lies on the amplitude at a resonance. So this is the way. For example, we can see here the harmonic response curve, which show half power point and bound with how we can, let's see. So this is the ratio x over st, which is sometimes we call magnification factor, mf. And in this direction, we can see omega over omega n, which is equals to r. We call r is equal to omega over omega n frequency ratio. Okay, frequency ratio magnification factor. So let's consider 2 points R1 and R2. Here there are R1 and R2 here. Okay, we have drawn a line from Q. Magnification factor is equal to Q over radical 2. Means Q over radical 2 means we have Q this. So Q over radical 2 means what? Which is equals to 1 over 2 pi 2 zeta, sorry, over radical 2. Okay, we can multiply this by radical 2 over radical 2, then finally we can get 2. So at this point, we can consider, we can find 2 values. One is here, another is here. Okay, so we call R1 and R2, and from here to here it is 1. From here to here it is 1. This is point of resonance. Okay, omega over omega n is equals to 1 means resonance line. We can observe resonance situation at this point. So the point where resonance takes place here, it is Q, which is equal to 1 over zeta. That is the what we called it as quality factor or Q factor. So Q over 2 is called half power point because the power absorbed delta W by the damper or by the resistor in the electrical circuit responding harmonically at a given frequency. So the work done or the power absorbed, which is equal to pi c omega x squared, because we derived this formula at the very early lectures. Someone can see this thing going back to lecture 2 or 3 like that. So these things are already derived. So power absorbed or work done, which is equals to pi c omega x squared. The difference between the frequencies associated with the half power point and is called the bandwidth. So this is the difference from R2 minus R1 gives us the bandwidth. So sometimes we call narrow band or wide band. So this is the bandwidth we call. So at this point, x over delta SCT is equals to q over radical of 2, which is equal to 1 over 2 pi radical 2. Okay? So this is the bandwidth. So let's see the situation at the point where this half power point. So we have x over delta SCT, which is equal to 1 over radical of 1 minus r squared the whole square plus 2 zeta r the whole square. This is from the general equation. Again now, from the half bandwidth, we have 1 over 2 zeta radical of 2. So we equated 2 different equations. Okay. Now, equating this term with this term, because this term and this term, we can get 1 minus r square the whole square under radical plus 2 zeta r square, which is equal to 2 radical 2 zeta. So squaring this part by this, again squaring both sides, we have this equation. Finally, we get r to the power of 4 minus 2 minus 4 zeta square r square plus 1 minus 8 zeta square is equal to 0. So this is a kind of quadratic form of equation with a value 1, b value is equals to minus of 2 minus 4 zeta square, and the c value is equals to 1 minus 8 zeta square, which is a quadratic equation of type. So for this, we can find R1 and R2, the quadratic roots, 2 roots of R. So R square, in terms of R square actually, because this is the power of 4. So R12 square, which is equal to minus b plus or minus radical of b square minus 4ac over 2a is the quadratic formula. Okay, applying this quadratic formula, what you can get the R12 values, which represents R1 and the 2 in the above diagram. So finally, we calculated and found R2 is equals to 1 minus 2 zeta square plus 2 zeta on the radical zeta square plus 1, and R1 is 1 minus 2 zeta square minus 2 zeta radical 2 zeta plus 1 in the radical. So this is the two R values. Okay. So this R value is this one, and this R is equation is this one. So this is what we have, what we call the quality factor Q and the bandwidth. So the difference between R2 and R1 will give us the bandwidth. So this is another lecture. So I will continue on the same PPT. Let's see. So what we are going to see is the response of damped system under the harmonic motion of the base. What we are talking here is harmonic motion of the base. We have a vibrating base, the base vibration. Okay. Still, we allowed the mass to vibrate. We allowed the structure to vibrate, and the structure transmits vibration to the ground before. Now the base transmits vibration to the structure. So so that is the situation which we are going to see here. Okay. So in this case, we have a kind of, for example, if the vehicle is moving in a rough road, which is full of humps and dumps, then that from the road, the system, the suspension system transmits shock and vibration to the passengers and to the equipments inside the car. So such kind of analysis will be analyzed here in this case. So we consider that the road and the system of road as a kind of having sinusoidal waveform of representation, and then how that vibration transmits shock or vibration to the structure or to the full system. That is what we are going to see. Okay, so in this case, this is the representation. This is the base. So we have a vibrating base or foundation. So we'll and this vibration will transmit to the structure here or the mass. So let's see, and the mass is having kind of acceleration like this, and the stiffness, the elastic nature of the structure is there, that is K. So we have kind of relative motion in between the two. The relative motion between the foundation and the structure, or the base and the structure. So that relative motion is equal to x minus y. Y is the motion, the profile of the kind of base excitation, how the base gives excite. So, and the x is the motion of the structure, the whole structure, or the car suspension system with the passenger. So that x motion and y motion here. So x minus y gives us the relative displacement, and also here relative velocity x dot minus y dot for the damper. So considering this and taking this free body diagram, this is free body diagram of the system. Okay. Free body diagram. Okay, taking this free body diagram, we have mx dot dot plus x dot c times x dot minus y dot plus k times x minus y, which is equal to 0. So this is the equation of motion. Okay, equation of motion. So expanding these terms and taking the y terms behind of this, what we have? Okay, sorry, here it is, this y is not there. This y is not there. So we have mx dot cx dot plus kx, which is equals to cy dot because of this and this, and ky because of this term. So we have mx dot plus cx dot plus kx, which is equals to cy dot plus ky. So this is the governing equation of this system. Now we have given the rod profile or the profile of the motion or base excitation, which is considered y of t is equal to y sine omega t, kind of sine amplitude. So it is given here. Therefore, y of t is equal to y sine omega t. That means y dot of t is equal to omega times y cos omega t. So we substitute these terms here and this term here. So immediately what we can get, mx dot plus cx dot plus kx. Still, this is my mistake. It is my mistake. So let me remove it, which is equal to cwy cos omega t plus ky sine omega t. So this is the equation of motion. Now, considering this part of equation as this cwy cos omega t plus ky sine omega t, considering this as a sine omega t minus some beta. Okay, some phase angle between sine and the cos beta. So then this a, the a is equals to cw y square plus ky square. Okay. Amplitude A is the amplitude this square plus, because the sine and the cos most of the time are in 90-degree difference. So if we consider this as some beta angle here, if this is sine, that is what we call it, ycw, okay, the sine component, okay, cwi, this becomes kw, no, ky, then this term is equals to this ky the whole square times plus c omega y the whole square. This is the hypotenuse. So the hypotenuse part is cwy square plus ky square, which is equals to radical of cw square plus ky k square times y, because y is a common. And the beta is equals to tan inverse of cw minus of cw c omega over k. Sorry, this w implies what I'm saying. W is the frequency. Okay, that is omega, not w. So this is the representation for this component. So substituting this thing, we have now the steady state amplitude of this type of equation, because as we know, we have derived formula for this type of equation. So the steady state amplitude, which is equal to F naught. Actually, this is for the function, forcing function F naught sine omega t case. So that directly resemble with, so in our case, it is A, not F naught width, instead of it is A. The A value is this one, okay? A over radical of K m omega square, the whole square plus CW square, sine omega t minus pi 1 minus B. This B is the sine and cos difference in the this equation. Okay, so that is different. So pi 1 is the phase angle of the whole transmission of the vibration. Now here our steady state amplitude becomes radical of k square plus cw the whole square y over radical of k minus m omega square plus cw square the whole square. So this is x, and phi, which is equal to pi 1 plus beta, this component, which is tan inverse of mcw cube over k times k minus m omega square plus cw. Actually, I can take out this k, so m over k becomes omega n. So we can make some arrangement here. So it is not as such. So let's consider this equation as whole x. So we have this x, okay, and this part as pi, so that sine omega t minus pi. So pi is this thing, and the x is this equation. Okay, so this is the response of this steady state response of the mass. Now the displacement transmissibility will come here, because we have here x is equals to some amplitude constant times y here. So x over y here represents the displacement transmissibility. It means that the relative displacement in between the base and the suspension system or the structure, which gives us the radical k square plus cw the whole square over radical of k minus m omega square the whole square plus cw c omega square. So finally we can get substituting the relation between damping coefficients and the zeta, and also the this frequency ratio, then we can substitute it 1 plus 2 zeta r the whole square over 1 minus r square the whole r square plus 2 zeta as the whole r square under radical. So this is the displacement transmissibility. Okay, so this is the ratio of the amplitude of the response to that of the base motion y of t is called the displacement transmissibility. So pi is equal to tan inverse of this. So we can represent this with the help of appropriate parameters like this. So we can evaluate those the relation between displacement transmissibility or versus frequency ratio in the relation to the damping ratios or damping factor. Okay, so for various damping factors, we can find various plots here. For very less damping, it goes to resonance. Here, what we are looking is the near to resonance point. Okay, here this is near to resonance point. This is omega over omega n is equal to 1, means resonance point. For if there is no damping, it will go for resonance. So for very less damping, we can see a lot of high overshoots. And when damping increase, it comes to damp. For example, if we see this graph, this is for damping zeta is equal to 0.25. And for zeta is equals to 0.25, we can see this graph. And all of these graphs come at one point here, which is in root 2. As we have seen there for the quality factor, and when we are talking about the quality factor and the bandwidth. So this is the point where all of these graphs intersect to each other. Okay. And another is the phase angle pi versus the frequency ratio. Okay. The phase angle pi from 0 to 180, and the frequency ratio 0 to some 3 or other number also comes. So on that we can see this type in relation to the damping. Okay. So these are the damping values. So the variation of TD and R in relation to damping. So this discusses about the condition of what is the transmissibility, what is the frequency ratio, how they are related. Someone can read this slide. So I don't want to read the slide one by one. So I invite you guys, you can read it. Okay, so now let's see the force transmissibility. Previously, what we have seen is the displacement transmissibility, or TD. Now, how we can check the amount of force transmitted to the structure. So force F is transmitted to the base or support due to reaction from the spring and the dashboard. The transmitted force to the base can be found as, we have these are the forces, K times X minus Y, C times X dot minus Y. These forces are the transmitted force, okay, which are equal to mass times acceleration in this direction. So F is equal to Cx, C times X dot minus Y dot plus K times X minus Y, which is equal to minus of mx. So we have x particular, which is x sine omega t minus pi, because we already derived these things, and x dot dot particular, which is equals to minus omega square x sine omega t minus pi. So we can substitute this equation into here. Okay, when we substitute this equation and this, what we can get is this equation, m omega square x sine omega t minus pi. This seems like kind of centrifugal force. Okay, the centrifugal m omega square r type, and centrifugal acceleration, which is equal to omega square r. So it seems like that. Okay, for actually this works for rotating unbalanced case with the centricity E, m omega square E. So so that type of equation we can observe from here. So F is equals to m omega square x sine omega t minus pi, which is equal to F transmitted. So this component is considered as Ft, that is transmitted force to the base. okay, from the structure to the base, where the amplitude or maximum value of the force transmitted to the base is given by this equation. So F transmitted is equals to m omega square x. Okay, so we know what is this x from our previous discussion, means we can see it back. So our x is this thing. This is our x, okay. We can leave y part and do, okay, x. We can see x here. So yeah, x is this term. This is x. So m omega square times this x. Okay. So from that, what we did here is we simply take out k from this equation. If k come out from here, again k come out from here. Both k, one of the k is related to its mass and this thing, because we need that omega n. Omega over omega n, it gives us. Means m over k means it is 1 over omega n square. And another k, with this came out from inside here, is related with y here. So ky here. Okay. So once k come out, k square over k square gives us 1. Again k over k 1. Yeah. And the k1 here is related with mass, which gives us omega n. Because of that, we have r square. So finally, we can get F transmitted is equals to r square, means omega over omega n is whole square, times radical of 1 plus 2 zeta r square times ky, the whole over radical of 1 minus r square, the whole r square plus 2 zeta r square. So let's bring this ky here. So ft over ky, which is equal to r square. Then actually we can use one root only for these terms, but we used it separately. Anyways, it is fair, no problem. So this equation is known as the force transmissibility. Ft over ky implies the force transmissibility. So we can see a graph of force transmissibility versus frequency ratio. Okay, to this frequency ratio and to this force transmissibility, or Ft over Ky. Okay, so in a relation to the damping factor. Okay, and someone can see it Ft over Me omega square. This belongs to the rotating unbalanced case. We can find the same. In the next lecture, maybe we can see the rotating unbalance. That means in the rotating machinery, if there is kind of small eccentric force, which is located at some eccentric distance E from the center of rotation, which produces the same transmissibility to the structure. Okay, so that is what we have. We are looking here. Now, what is the relative motion? So as we have discussed that early in our discussion, so x minus y is a relative motion, which is z is equal to x minus y. So which denotes the motion of mass relative to the base. And the question of motion can be, this is the question of motion, okay? Then we substitute this x means from this relation x is equal to z plus y. So x dot dot means z dot dot plus y dot dot. Okay. Then finally we can get this equation. Means x dot minus y dot is equal to z dot. X minus y is equal to z. But x dot is equals to z dot plus dot plus y dot dot. Then finally, rearranging what we have, mz dot dot plus cz dot plus kz is equal to minus of my dot dot. And our y is already given in the from the road profile. Y of t is equals to y, capital Y, sine omega t, so that this y dot dot means the acceleration term of y dot of t is equals to minus of omega square y, capital Y, sine omega t. So that substituting this here, we can get mz square plus cz, mz dot dot plus cz dot plus kz, which is equal to m omega square y sine omega t. This is the equation of motion. And then the solution for this z of t, the solution z of t is equals to m omega square y, this term, that means f naught term, m omega square y, the whole over radical of k minus m omega square, the whole square plus cw the whole square sine omega t minus pi 1. So this implies z of t is equal to z sine omega t. So this amplitude z sine omega t is equals to this equation. Okay. This is this relation. And in terms of a reduced form, r square y over 1 minus r square plus 2 zeta r whole square in the radical, so which gives us so this z over y, which is the relative motion. Okay, z over y is the relative motion of the thing. So this is the expression for z over y, and the variation of z over y, or in the rotating unbalance, we have mx over me. This relation are represented here in the diagram. So here we can see z over y, or base motion, or we can consider mx over me. M is the bigger mass of structure. Small m is the smaller mass, which makes vibration, or which located at eccentric and distance. E is centricity. X is the amplitude of motion. So this is for rotating unbalanced case. So this is the relation between. Now, once we understand this, we can take some practical problem. We have to solve some problem based on the above discussions. So what are the problems? So let's see the vehicle moving on rough road. That is the best example for the previous discussion. Look, this is a rough road having a sinusoidal profile. Okay, this is a sine profiled rough road. This is the car suspension system, and the car is moving with some velocity v, and having a suspension system having a stiffness k, and the damping system with damper c. Okay, and so this is the representation. We have given mass of the car, the total system mass is equal to 1,200 kg. The stiffness K is equal to 400,000 Newton per meter. Damping ratio, the damping ratio zeta, which is equals to damping coefficient C over critical damping coefficient CC, which is equal to 0.25. The velocity of the car given 50 km per hour, And the maximum amplitude of this rough road is considered 0.1 meter or 10 centimeter. And the wavelength of the road profile means the distance that from one peak to another peak, or to complete one full cycle, the distance to complete one cycle known as the wavelength, which is 5 meters, and required the steady state amplitude of this motion. So let's search for the let's calculate. So the frequency of the base excitation can be obtained as we have to find the frequency, because frequency F is equal to speed of vehicle over wavelengths. Okay, so wavelengths of the road profile, lambda. Okay, so V is given, lambda is given. So we put these values, and we have to convert the velocity B into meter per second form, because this 50 kilometer per hour means it is. So we can divide this by 3.6 actually. If it is given in kilometer per hour, in order to use the SI unit, we have to divide the given velocity by 3.6, so that we have 13.889 meter per second, the velocity of the car. Okay, the frequency F is equal to V over lambda, which is equals to 2.778 hertz, and we have to convert this frequency to the angular frequency omega. Okay, so angular frequency omega is equal to 2 pi f. From that we can get 17.4533 rad per second in the angular frequency. Okay. Okay, so the natural frequency of the system is directly obtained, that is, it is under radical k over f. So immediately dividing this, we can get 18.2574 rad per second. So just observing two values, the operating frequency or rotating frequency of the system frequency, and the natural frequency of the system here. This thing is operating near to each other. Okay, 17.45 and 18.25, they are very near to each other. So designer must consider those things. If frequencies, both frequencies are coming to near each other, the condition of resonance will occur. Okay, so even the frequency ratio of omega over omega is equal to 0.956. This is almost near to 1. So designer must take care of his design by checking the different parameters, at least by reducing some maybe speed also, their wavelengths already this road profile, so that some mechanism must be drawn for such case. It is near to resonance condition. Okay, so this is the frequency ratio. Then the amplitude ratio is directly from the equation developed in the previous discussion. From this, we have zeta, which is given, r is given, so that we substitute these values in order to get x over y. So from that, 2.282 is the amplitude ratio, or what we call. Okay, now displacement ratio, or TD. We call this TD, displacement transmissibility. From that, we have given y is equal to 0.1 meter, that is from the road profile, so that immediately substituting in y, we can get x is equal to 0.2282 meters. This is what we are going to calculate. So let's conclude what it seems like. In the above case, the values are 0.1 meter or 10 centimeter bump in the road is transmitted as 0.2282 meter, which is 22.85 centimeter bump to the chassis and to the passenger inside the car. That means high amplitude is transferred. So the passenger and the system will get vibrate or get shock. So thus in the presence, this passenger feel an amplitude motion. Okay. The passengers can detect or feel the vibration. So our aim is to eliminate such kind of vibration or to avoid the discomfort of the user. So this gives us the kind of discomfort so that we have to take care of this thing. Another second question is motion or resilience of foundation. Okay. So we have given this parameters. We can directly find this example on SS Rao vibration book. So it says a heavy machine weight 3,000 Newton is supported on a resilience foundation. The static deflection of the foundation due to the weight of the machine is found to be 7.5 centimeter, that is delta S T. It is observed that the machine vibrates with an amplitude of 1 centimeter, and the base of the foundation is subject to harmonic oscillation at the undamped natural condition of frequency of the system, with amplitude of 0.25 centimeters. So this undamped natural frequency, when we say this, that is at the resonance condition. Okay. So find the damping constant of the foundation, the dynamic force amplitude on the base, and the amplitude of the displacement of the machine relative to the base. So what we are going to find is the damping constant C, the dynamic force transmitted, and the relative amplitude. So these are the questions. So let's see. Now we have given actually stiffness is not directly given there. It is we have given only the mass and the static deflection, the weight and the static deflection, so that K is equals to weight over delta ST, or we know delta ST is equals to static deflection ST is equals to F naught over K. F naught over K. Like that. So K is equals to F naught over delta ST. That F naught is, in our case, our F naught is the weight of the foundation. So K is equal to weight over delta ST. From that, we can get 4,000 Newton per meter. And also, the mass of the foundation is weight over gravity, so that we have this kg. Sorry, this is in kilogram. Mass in kilogram. And at resonance point, which omega is equal to omega n, we have x over y, 1 plus 2 zeta square over 2 zeta square. So from that, we can get x over y is given, means x is 0.01, 1 centimeter. Okay, and y is equals to 0.25 centimeter. Okay, yeah. So substituting these values, 0.01 over 0.025, this is equals to 4. So we can get zeta. 4 is equal to this equation, means zeta value is 0.1291. So the damping factor, zeta is equal to C over Cc. So from this, and this CC is equals to 2 radical Kn. Okay? So C is equals to zeta times CC, which is equals to 2 times zeta times radical Kn. That gives us the damping coefficient 903.0512 Newton second per meter. This is the damping coefficient. The dynamic force amplitude on the base at R is equal to 1, this at resonance, this means resonance point, can be found from Ft over Yk is equals to this value. So, which is equals to Kx. Okay, so by substituting these values, Ft is equal to Yk. So Y is known, K is known, and these values are also known. So we can substitute this thing, or we can use directly Kx. So it is this amount. And then finally, the amplitude of the relative displacement of the machine at R is equal to 1 can be, which is Z over Y is equal to 1 over 2 zeta, which is in the quality factor condition. Okay. This 1 over 2 zeta is Q actually. So Z is equal to Y over 2 zeta. So from that we can find 0.00968 meter, or which is equals to 9.68 millimeter. So this is Z. So it can be observed that X is equal to 0.01 meter, Y is equal to 0.0025 meter, and Z is equal to 0.00968 meter. Therefore, Z is different from X minus Y. If we subtract X minus Y, it gives us we can see what it is. So it is different. It will not give the same value as Z value that we have here. Okay, our X minus Y is 0.01 minus 0.0025, which gives us 0.0075. It is not 0.0096. Means X minus Y is equals to 0.0075. That is Z. But here Z value is 0.00968, which is different from this value. So that shows due to the phase difference between X, Y, and Z. This happened because of this. So this is all about today. So we'll see response of damped system and the rotating unbalance in the next lecture. So thank you for paying attention for this lecture. Okay, so this is all about